now going to look at unit operations for exergy analysis. So we're going to use your slides so that you can easily understand and have reference. So unit operations are basically, we're going to look at units. These units include turbines, pumps, heaters, heat exchangers, mixers, etc. So we're going to look at how you can calculate the exergy, how you can analyze the exergy within those units. Okay, so this diagram just shows you, it's just showing you the exergy flow that is going out, the available work that is going out, the work that is going out, also the heat losses. Yeah, the same this side. Then it's just explaining this is the equation for the irreversibility, which is the negative irreversibility is equal to change in the flow process free energy plus the change in available work plus the change in work. So this is the available work free process, this is a free process, this is the free energy from the process flow, this is the available work, and this is the work. Then what it's saying is the efficiency is equal to the free generated, which is the free energy generated over the free energy consumed. So the free energy generated is what you are using. So the energy that you are using, let's say if you're using the energy, this energy, well, that is going in, we want to use it to create some heat or to heat a room. It means that the free energy that is being generated is the heated energy, and then the free energy consumed is the difference between the energy that you're putting in and the energy that you're taking out, which is just an example. We're now going to look at an adiabatic turbine. So an adiabatic turbine is the one without pressure losses. So for an adiabatic turbine, what we have is we have a process flow that comes in and we have a process flow that comes out. From this process flow we derive work. That is how it always is for a turbine. Okay, so to find the irreversibility, we use this equation where the change in irreversibility is equal to the change in the free energy due to process flow plus change in available work plus change in work. So this is the change, this is the process flow, free energy, then this is the work. So we do not have available work there, so we cancel out the available work. Okay, so here this is where they found the change in process flow free energy, which is equal to out minus in, which is 8 minus 25, which gives us negative 17 kilowatts. And like I said, the available work here is not there, so we just say it's equal to 0. Then the change in work is work out minus work in, which is 11, which there's no work in, which minus 0, which is 11 kilowatts. So it means that the irreversibility will then be equal to negative 17 plus 11, which is equal to negative 6 kilowatts. That's the negative irreversibility. So the irreversibility is 6 kilowatts. So meaning in between this process here, the free energy that is lost is 6 kilowatts. So this side just shows the other way in which we could have done it instead of considering it one by one. What we would have just done is we would have just said irreversibility is equal to everything that's coming in minus everything that's going out. So what's coming in is 25 kilowatts, and what's going out for this is the only thing that's coming in, this flow, this process flow, and then this is going out, which is the 11 kilowatts and the 8 kilowatts. So when we find in the irreversibility, it's going to be what's going in minus what's going out, which would be 25 minus 19, which is equal to 6 kilowatts. Then we're going to have the second law efficiency. This is how you find the second law efficiency for all turbines. So for a turbine, like I said before, the second law efficiency is equal to free generated. So the free energy generated is the energy that we want to use, or what we are getting out for our use. And then the free energy consumed is the energy that we use up to create that which we want. So for this one, for the turbine, the generated work, obviously we always look for shaft work from a turbine, so it will be the work out, which is 11 kilowatts. Then the consumed energy is a free energy which comes in minus the free energy which goes out, since we get this work from the free energy that comes in from the process flow. So from here it will be 25 minus 8, which is 17 kilowatts. So the free energy that is used up here is 17 kilowatts, but only 11 kilowatts is produced here as work. Therefore, for the second law efficiency, it will be 11 over 17, which means that this turbine is 64.7% efficient. This slide shows a non-adiabatic turbine. So a non-adiabatic turbine has got heat loss. So whether it's an adiabatic turbine or non-adiabatic turbine, we use the same formulas, we use the same equation, nothing changes. We do not add this to kilowatts anywhere, we do not add the Q loss anywhere. What we just focus on are the process flow in, the process flow out, and the work out. That is what we use to calculate the irreversibility, and that is what we also use to find the second law efficiency. Nothing else. That is for a turbine. Then if it is a compressor or a pump, we just do the opposite way. If it's a compressor or a pump, because for a pump we put in work. When we put in work, that's when we get a greater free energy in the process flow. So we just do the opposite way. Then we also interchange the values for the work and the difference in process flow when finding the efficiency. That is for a turbine or a compressor. Sorry, that is for a compressor or a pump.